and welcome to this week 2 of MATLAB programming for numerical computation course. In this module, we are going to cover errors and approximations. This is lecture 2.1, and in this lecture, we are going to look at where do errors originate in numerical methods. One of the things that happens always when we talk about numerical methods, when you use computers for using numerical techniques, you will always encounter errors of various forms, and these errors are going to have two basic origins. One is what is known as truncation errors, and the other is known as the round off errors. Where do these errors come from and how do they affect the overall numerical methods is something that we will introduce ourselves to in this particular lecture. Okay, so let us look at the first type of an error, that is called the truncation error, and what I have listed over here is the Maclaurin series for calculating e to the power x. The Maclaurin series for e to the power x up to nth order term is written as 1 e to the power a, is written as 1 plus a square by 2 factorial plus a cube by 3 factorial and so on. So, what we are going to do is we are going to compute e to the power 0.1 using multiple number of terms in this Maclaurin series, and we will compare it with the actual value. The error we will define as the difference between the true value and the approximate value. We do not care whether this difference is positive or negative. The error is therefore just the absolute value of the difference. So, it does not matter whether the approximate value is greater than or lesser than the true value. As long as it is different than the true value, we want to capture how much that difference is, and that is how we define the absolute error epsilon. Okay, and what we will show using MATLAB is that if we introduce more number of terms in this Maclaurin series, we are going to get lower error. Okay. So, let us head on over to MATLAB in order to compute this using the Maclaurin series approximation. So, let us open a script file, let us call it Maclaurin exp. Okay, we will create the file Maclaurin series for exp of 0.1. Okay. So, let us look at Maclaurin series with different number of terms. So, let us say we want to look at terms up to n equal to 5. So, we will say n equal to 5, our value of a was 0.1, okay, and the result, that is, let us call this as exp val equal to 1.0. Why 1.0 is the first term over here is 1, the first order term, that is a to the power 1 term is a to the power 2 term is a square divided by 2 factorial, so on and so forth. So, if we look at the first term and compare it with the second term, the first term is just multiplied by a divided by 2. If we compare these two terms, it is just multiplied by a divided by 3, so on and so forth. So, that is what we are going to do. We will call current term as 1.0, and we will use a for loop for I equal to 1 to n, okay, and current term equal to current term multiplied by a divided by I. Okay. So, let us see how exactly this works. So, we have e to the power a that we need to compute approximately when I is going to be equal to 1. At that time, our value of current term is going to be 1 multiplied by a divided by 1, that is a. In the next loop, it is going to be a multiplied by a by 2, that is a square by 2 factorial. The next term will be a multiplied a by a square by 2 multiplied by a by 3, that would be a cube by 3 factorial, so on and so forth. Okay. And our exp val equal to exp val plus current term. Okay. And I will end this loop over here. So, that is going to be the value of exp val. Let us say true val equal to exp 0.1 and error equal to abs true val minus exp val. Okay. So, we save this and we will run. Let us go to MATLAB and run it, and we get this result. So, we actually see that the error is 1.4 multiplied by e to the power 10 minus 9. That is the error. Exp val is 1.1052 and true val is also 1.1052, because the error is of the order of 10 to the power minus 9. Okay. Now, what let us do this is let us change the particular code so that we store all the various values of exp val. So, let us say exp val I equal to exp val I minus 1, or let us put it this way, exp val I plus 1 equal to exp val I plus current term. So, what does the first exp val contain? It is the 0 ordered approximation, that is just 1. So, that is not really an approximation. Exp val 2 is going to have 1 plus a, exp val 3 is going to have 1 plus a square by 2 factorial, so on and so forth. When we calculate this error, true val is a scalar and exp val is a vector. So, we can subtract a scalar from a vector or a vector from a scalar, and we will get a resulting vector. So, this should not be any problem for us. The error will actually end up being a 6 dimensional vector, a 1 by 6 vector. Okay. So, let us go ahead and clear. Okay, and let us now run Maclaurin exp. Okay. So, now we have the error, and as you can see, the error is 10 to the power minus 3, 10 to the power minus 4, and as we go to higher order terms, the error keeps decreasing quite significantly. So, what we see over here is that as we introduce more and more terms, our error keeps decreasing quite significantly. Okay. So, let us look at error 4, which is basically when n equal to 3, our error is 10 to the power minus 6. When n equal to 4, our error is going to be 10 to the power minus 8, and we have seen already that when we introduce all 5 terms of the Maclaurin series, our error drops even further. Okay. So, this is how we have computed the e to the power a approximation using Maclaurin series. So, what we have seen over here is that as we truncate the overall series to nth order terms, we realize that the error keeps on decreasing. So, more the number of terms of the Maclaurin series we introduce, the smaller is going to be the error. Okay. Why does the error keep changing, or why is there an error in the first place? The reason why there is an error in the first place is because we are truncating this Maclaurin series. So, this series is being truncated at the first term or the second term or the third term and so on and so forth. If we truncate it just to the first order term, we are going to get a greater amount of error. The error was of the order of 10 to the power minus 3. When we truncated it to second order term, we got error of 10 to the power minus 4. When we truncated it to the third order term, we got the error of the order of 10 to the power minus 6, so on and so forth. So, what we saw over here is that once we introduce greater number of terms, we are going to reduce the error. This is going to be something that is going to we are going to see consistently in this particular course. So, if I can summarize these results, what these results are is when you have an infinite series, the greater number of terms that you retain in the infinite series, the greater is the accuracy, or conversely smaller is the error. Okay. In the next lecture, we will expand this particular idea to Taylor series expansion. Taylor series expansion is indeed where we get this Maclaurin series from. So, that particular idea of introducing more number of terms in order to reduce the overall truncation error is going to be a common motive that we are going to follow in the rest of this particular lecture series. Okay. So, this was the first type of an error, which is the truncation error. The second type of an error turns out because of what is known as machine precision. We like to think of a computer as having what is known as an infinite precision. However, that is not really true. The machine, the computer also has a machine precision, which in some ways is like a least count. So, let us consider a ruler that I have shown over here. The least count of this ruler is 1 millimeter or 0.1 centimeter. So, that is kind of the minimum resolution of that ruler. You cannot measure length that is less than 1 millimeter. Okay. If you want to measure length with a precision greater than 1 millimeter or a precision value of sub millimeter, we can for example use a vernier calipers. This particular example of vernier calipers has a least count of 0.01 centimeter. So, we can say that this vernier calipers has a better precision than a ruler. Okay. So, precision is basically a term which we can approximately we can use it in lieu of the term least count. Okay. So, it is kind of like least count. Now, in the same manner in which these two devices have a least count, our computer also has a least count. Okay. Just like these devices, the real numbers in a computer representation have a least count. So, between a number a and a number a plus epsilon, there does not exist any number, and that is what the machine precision is about. It is about the least count of that particular computer. Okay. And that least count is dependent on the number of bytes that we use in order to store a real number. So, for example, a standard real number is uses 4 bytes, which is basically 32 bits. So, that particular real number has a certain precision. A double precision real number which uses 8 bytes or 64 bits has a better machine precision. Okay? And that representation is based on what is known as the floating point representation of a number. For more information on this, you can go to the computational techniques course, the link for which is given over here, and look at the machine precision and floating point representation. So, let us look at floating point representation of a decimal number. Let us say we have 5 boxes in order to store a number and 1 box in order to store an exponent. Okay. The number is always going to be represented as 0.xxxxx multiplied by 10 to the power n. Okay. So, this is where we put in those 5 digits of our decimal number. So, let us see how we represent a number of 23.217. The number 23.217 becomes 0.23217 multiplied by 10 to the power 2. So, what is the next number that comes in? The next number is when the lowest digit over here is incremented. So, that becomes the next number becomes 23218 multiplied by 10 to the power 2. That is the next number. Okay. So, what if we had a number of the form 23.2172? The problem is that when the number 23.2172 cannot be represented with 5 digits of what is known as mantissa and 1 digit exponent. The reason is that number will be represented as 0.23217 multiplied by 10 to the power 2. There is no space to store this trailing digit. Okay. As a result, this number and this particular number have the exact same representation. The reason why we are not able to represent a number with a 6th significant digit is because we do not have enough precision in our decimal machine. Okay. So, the least count of this particular decimal machine turns out to be 10 to the power minus 5 multiplied by the absolute value of x. So, that is this 10 to the power minus 5 is what is known as the machine precision. In case of MATLAB, the machine precision is given by a keyword EPS, and the machine precision in MATLAB is 2 multiplied by 10 to the power minus 16. Okay. This machine precision is 2 to the power minus 52. The reason is because just the way we had 5 digit representation of this mantissa in this decimal number, likewise the double precision real number that MATLAB uses, which is the IBM standard, uses a 52 bit mantissa. So, the mantissa has 52 bits in it. So, the precision is 2 to the power minus 52. Note over here that the precision was 10 to the power minus 5. Okay. So, let us look at the case where we have, let us call A equal to 1 plus 2 to the power minus 52. So, okay, that is the value of our A, and if we subtract A minus 1, we are going to extract this particular value. Okay. So, what is happening over here is when we use the value of this precision, that particular number A 1 plus 2 into 10 to the power minus 6 is indeed represented as 1.00015 times followed by a 2. However, what if we write A equal to 1 minus 2 to the power minus 53? This number is going to be indistinguishable from 1. If we say A minus 1, we are going to get a result of 0. Okay. So, what does this mean is, this means that our MATLAB has a least count of 2 to the power minus 16, and that is what is known as the machine precision. Okay. So, with this we come to the end of this particular lecture. In this lecture we covered two important concepts. The two concepts that we covered in this lecture were, one is that the truncation error, because we are going to truncate an infinite series to a finite number of terms, there is going to be an inherent error that is associated with that truncation. The second thing that we realized was that there is a machine precision. We cannot represent any real number in any form that we want. There is going to be a least count with respect to representing those real numbers. So, what does this imply when it comes to numerical techniques is something that we are going to cover in the next lecture. Thank you and see you in the next lecture.